Let's have a look at this task 27. So we have a simple, not too complicated circuit. We have a voltage source, and there we have square root of 2 times 230 volts as the amplitude, and 30 degree of phase shift. So where do we usually have this RMS value? It's our mains power outlet. And so this would be the RMS value. The RMS value multiplied with square root of 2 would be the peak value, would be the amplitude. Okay, and so connected to our power outlet, we have a ohmic-capacitive load. So we have some resistor and we have some capacitor. And we know that the resistance is 23 ohms and 1 over the angular frequency, and the capacitance is also 23 ohms. We can check during the calculation that this also works from the unit. And so now we should calculate different things: complex total admittance and impedance of the load, the currents using the voltage, the total current by adding this, and the currents using the the current divider rule, of course, because it's a parallel circuit. And this all using our complex quantities, complex phasors, and then we should draw a phasor diagram in the complex plane. And okay, maybe before we do this, just to show that it would be possible, we could also try to do this without using complex phasors at all. So this voltage here is, of course, also across the resistance, and the same voltage across the capacitance. So if we know the voltage and if we know the resistance, how could we calculate the current through the resistance or through the resistor? V by R. So we take this time function and we divide by R. And so then we can check, okay, R is just a value, 230 volts divided by 23 ohm, volt divided by ohm gives ampere, and the remaining number is 10 in this example. So we get something like square root of 2 times 10 ampere times the same sinusoidal function omega t plus 30 degree. Okay, so this is solved. How can we calculate the current through the capacitor? What is the relation between current and voltage at some capacitor? How is capacitance defined? Say again? 1 over R? No. Yeah, from this equation, it looks like, no, but I mean, then there's still this omega included. So C is not, yeah, okay. From this equation, we could say, okay, C in this case is 1 over R and omega, but this is just for this equation. But very general, what is the definition of the capacitance? Yeah, it's the charge that we have somewhere, and that might also change over time, divided by the voltage that we need to have this charge on a certain capacitor. And so, okay, so then now we have capacitance, we have voltage, and we have charge already. How are charge and current related to each other?
Charge is current divided by time.
Yeah, or we could say the current is the time derivative of the charge. So if the charge changes over time, then we have a current flowing. And so now we could insert our equation for the charge there. and now we get C multiplied with the time derivative of the voltage over time. And so now we need to insert our voltage function that we have here and calculate the time derivative. And we need to multiply with C. Okay, so C multiplied with, then I will just copy this, square root of 230 volts, because this is some constant factor that we can just write before this time derivative. And what is the time derivative of the sine function? It's a cosine function. So a cosine function of the very same argument, and we calculated the time derivative with respect to time, but inside our cosine function we just not only have the time, but we have some factor before the time. We have some nested function. This is the derivative of the outer function, and we need to multiply with the derivative of the inner function. What is the derivative of this inner function with respect to the time? Just omega. So we need to multiply with omega. And otherwise it also would not make sense in terms of the units, as we will see in a second. Okay, so now we know, okay, omega times C is like 1 over 23 ohms. So instead of omega and C, or C and omega, I could also write or divide by 23 ohm. Ohm is again volt divided by ampere, so the volts will cancel each other. 23 will cancel each other, and we also get in this case 10 ampere, no, square root of 2 times 10 ampere. Square root of 2 times 10 ampere times the cosine of omega t plus 30 degree. And yeah, so now we have time, the time function of the current through the resistor, the time function of the current through the capacitor. So now, of course, we could also write something that the total current is, if we take Kirchhoff's current law at this circuit, the total current is the sum of the partial currents, or the sum of these individual currents. And so then if we would like to do this calculation, we kind of get a problem in this case, because we have the sum of a sine function and a cosine function. And yeah, it's somehow possible to calculate this in this case. So if we would like to have the sum of this sine and cosine function, any idea to do this? And so I will shortly check my browser and say Formelsammlung Trigonometrie, and then there should be a nice Wikipedia page. And so there is, it's a German one, but we can also try to find an English thing. So if you have the sum of a sine function and a cosine function with the same argument, but just with different magnitudes, in our case, they would also have the same magnitude, then we get something like this. So as we can see, it's the square root of a squared and b squared, and then yeah, the sine function plus the arcus-tangens of the ratio between the two. And so in our case they are equal, because it's both square root of 2 times 10 ampere. So this arcus-tangens, the argument of this arcus-tangens is 1 if the argument of the arcus tangens is 1, what is the value of the arcus tangens function? If you have, if we go back to this schematic, if real part and imaginary part are equal, it's 45 degrees. Yeah, so we get, and here they are also equal, so we get another square root of 2. So our total current in this case should be square root of 2 times square root of 2 gives 2. 2 times 10 is 20 ampere times, and yeah, so then it said if A is larger than 1 and A is larger than 1 in our case, so we take the sine function of A of the same argument plus 45 degrees. So we take the sine function of omega t. We already had 30 degrees, so we add 45, so we end up with 75 degrees. This should be our total current that we get. And now we have done the calculation just in time domain. It's, yeah, the last step is somehow tricky, and the step here is also somewhat tricky because we need to calculate this time derivative. And if this would be some inductor, for example, then we would need to calculate some integral in this case. And in general, we would need to solve differential equations, and we don't want to do this. Yeah, so this way works here because the circuit is so simple, but this way would not work in general. Or in general, this way would be quite complicated. Okay, so now the idea is, instead of using these time functions, we use complex phasors, and we use complex impedance and complex admittance. So I will use a different color for this subtask A. And so now instead of IR of t is, no, maybe let's write it in a different way. We'll start with the voltage. Instead of writing the voltage at the resistor as a function of time is the resistance times the current through the resistor as a function of time, we would like to rewrite this in the frequency domain with complex equations. And how does the equation look like in this case? And in this case, it's super simple. And yeah, so what we do is, let's maybe invest in, no, maybe I can write this here so then we have it on the same page. So now instead of this equation, and this is somehow the connection to the task that we have done before. So instead of this here, we could also write it's the real part of square root of 2 times 230 volts times, no, and in this case it's not the real part, it's the imaginary part. But does not change anything. So the imaginary part of this, and then E2J omega t and E2J 30 degree, right? Because the product of two exponential functions is like the same as if we would have the sum of these exponents. And if we just take the imaginary part of this complex function, then we would get the sine function. So this here looks different, but at the end, from a mathematical point of view, is the very same as we have written there. And so now I could also combine this and say it's the imaginary part of, and so let's take green maybe once again. So now I will combine this and this together and call this complex voltage phasor. But It's a peak phasor, so it's lowercase. And this is then still multiplied with e to j omega t. And our v in this case, as we can see, is square root of 2 times 230 volts times e to j 30 degree. So this short derivation here, this formula, this is the relation between the complex phasor and the time function. Let's say more from a mathematical view as what we have done here, because here we have just rewritten it. Yeah? And so here it's written how they really belong together. And as said, this function looks different, but at the end it's the very same thing as above there. Okay, and so now we could take this equation and insert it here. Take a very same equation for the current and insert it here. And then do some manipulation. And at the end, we would find out, okay, this equation, if we insert this stuff into this equation, long story short is the complex voltage phasor is the same as the resistance times the complex current phasor. So Ohm's law for DC currents, for time functions, for complex phasors looks exactly the same. Okay, so maybe where it's more interesting is to check what happens for the capacitor. And so I think for this I need a new page. So we are still at task A. So for the capacitor, we said that the current through the capacitor is C times the time derivative of the voltage drop. So now if for the voltage, if I insert this what we just said, so no, this equation here, let's say, or maybe this equation, this is simpler. Confusing the pages here. So this is the real part of our complex voltage phasor multiplied with e to j omega t, and then time derivative with respect, or derivative with respect to the time. So how do we solve this? This complex phasor does not depend on time. It's a stationary phasor. There's just amplitude and phase in there. So we can move this out of the time derivative. And we can also change the order between the time derivative and the real part. If you calculate the derivative of the complex function first and then take the real part, or you take the real part first and calculate the time derivative, does not make any difference. So at the end, we just need to have the time derivative of this complex function. And what is the derivative of a complex function? Or no, of the exponential function? It's the exponential function. But we calculate the derivative with respect to the time. But in the argument, we also have j and omega. So the result here is, okay, we get C times, So at the end we get j omega, the multiplication with j omega. We still have C, and then our time derivative is gone, and we still have the V. But that we still need inside the real part, so we let's write it like this. So we have the real part still of V times e to j omega t. Okay, so now if we would also write this current function in this way and then do some comparison, we would find out that this equation in time domain turns into complex current phasor is j omega c times complex voltage phasor. Yeah, so if you would, for the time function of the current, insert what we had before, something like this here, and just check that you get the both on same sides, you would get this. And so now if we write this back into voltage, depends on current, then we would get 1 over j omega c. So this is the same as what we had before. So for the resistance, we had voltage. Maybe I will write resistance here at the end. Voltage is resistance times current. And here we get 1 over j omega c. If we would do the same thing with some inductor, for some inductor, we get voltage as a function of time is inductance times time derivative of the current. So for some inductor, then we would, yeah, if you do this, now we will get the multiplication with j omega here. So for some inductor, we would get V is j omega L times I. Okay, and so now, how do we call this here, or how do we call this here, or how also in the general case, how do we call this? That relates a current to a voltage. Some term that appears here in our exercise task. This is impedance, exactly. So this means impedance. So this here we would call ZZ, or this is what we would call ZL, or this is what we would call ZR. And these impedances are usually complex. And so the opposite thing, this here, that relates a voltage with the current, this is what we would call admittance. So this is the admittance of a capacitor. This is what we call Y, Z and Y. And with these impedances, so impedances are like a resistor, but just complex. And these admittances are like a conductance, but also just complex. And with them now, we can try to calculate our circuit here. So because now if we have impedance and admittance, and if we have these complex phasors, now the advantage is everything that we have learned before from DC circuits with Kirchhoff's current law, Kirchhoff's voltage law, let's say Ohm's law, but in a complex way, voltage divider, current divider, mesh current analysis, branch current analysis, nodal voltage analysis, superposition theorem, everything works as before, just we need to use complex values. Okay, so then we can now really start with subtask A and say what is the complex total admittance and impedance of the load. So maybe we start with complex admittance because it's already also written in a way. Because we have a parallel circuit. If we would have two resistors in parallel, how would you calculate the total conductance in a parallel circuit? It's just the sum. And so in our case, it's just the total admittance is just the sum of the admittance of the resistor plus the admittance of the capacitor. And so the admittance of the resistor is 1 over R, and the admittance of the capacitor is omega C, or no, better j omega C. Yeah, because this is just what we have written on the second page here. This is the one for the capacitor, and the one for the resistor is 1 over R. Okay, so I will go back to my Octave window, which is there, and maybe say for a moment clear all and close all, or CLC. Okay, so R is 23, so YR, the admittance is 1 over R, no problem. Okay, and then we set 1 over omega C, this is what I will call XC. It's also 23 ohm, and so this YC, this is the X is what we will call reactance. Yeah, it's now just a question on how do I put these numbers there into my Octave. But the YC should be 1J also divided by this XC. And so at the end, of course, resistance and capacitance, they both have the same value here in ohms, so we should also get the same value there for the admittance. This is real valued, this is complex valued. What would be the unit of this? Yeah, 1 over ohm, and this is Siemens. Okay, so it's 43.5, let's say, millisiemens. So we can say this is 43.5 millisiemens plus J 43.5 millisiemens. Okay, this is complex admittance. How do we get complex impedance? If we look at the second page, how are admittance and impedance related to each other? The inverse, or let's say the reciprocal value. So if we take 1 over y, we get z. And this is super simple here. So I take 1 over y and I get z. And y is not defined yet because I've not calculated the sum. So y is yr plus yz, and then z is 1 over y. And we get 11.5 ohm minus j 11.5 ohm. Okay, questions so far? The solution of task A. Before we maybe continue with task B, a quick remark to task A. How could we also possibly calculate the impedance of this parallel connection here? How could you also calculate the equivalent resistance of a circuit of two parallel resistors? If you have R1 parallel to R2, how could you calculate the total resistance?
R1 times R2 divided by...
Yeah, the product divided by the sum. So if I write down my usual parallel function here, so a function that depends on, not now in this case not R but Z, but of course it's just a name, so it's the same, the product divided by the sum. And if I would write my, if I would rewrite the YR into a ZR, yeah, and the ZR should be just the resistance, should be just 23 ohm, and the ZZ is 1 over JZ, should be minus J 23 ohm, because 1 over J is the same as minus J. This is something fundamental that we should have also discussed in the previous task. 1 over j is the same as minus j. And now if I put them into this parallel circuit and say the parallel connection of ZR and ZZ, then we get the same as we had before. Scroll up. So there is the result that we had before from our admittance calculation, and with the parallel connection we get the same. Yeah? So this is what I mentioned. Remember all what we did with resistive circuits? Everything now applies that you need to calculate with complex numbers. And the problem of calculating with complex numbers is not a problem if you can use MATLAB or Octave, because there everything works internally. You just need to use these formulas. Okay, so we have calculated total admittance and total impedance of the load. So now how can we calculate the currents using the voltage? How do we get the current through the resistor and the current through the capacitor and so on? So maybe I will take blue once again for this task B. So if I want to have the current through the resistor, how can I calculate it? V by R. So we take our complex voltage phasor, we divide by R. The current through the capacitor, we take our voltage, we divide by the impedance of the capacitor. Or here I could have also written not R but ZR. And so how do I get the total current? IR plus IC, or I could also take the voltage and divide by the total impedance that we just calculated before. Yeah, or I could of course also say, okay, this is the voltage times the admittance, or this is the voltage times the admittance of the capacitor, or this is the voltage times the admittance of the whole circuit. And so then let's do this in Octave. So IR, I think we need V first. So V was square root of 2 multiplied with 230 and then multiplied with the exponential function of 1j times 30 degree divided by 180 multiplied with P. So this should be our complex voltage phasor, and so then we can calculate the current through the resistor as the voltage divided by ZR. And we get this value. I think I won't write it down now because yeah, it's just saved into MATLAB. It's probably also in this way easier to do it in this exponential form. If you would write it down, yeah. So if we would insert the equation from before, yeah, this one here divide by 23 ohms, then we should in this case also get square root of 2 times 10 ampere times E2J 30 degree. And if we check what we have just calculated here, if I take the absolute value of this IR, then we get this square root of 2 times 10. And if I calculate the angle of this as we have done before, multiply with 180 divide by P, then we get also the 30 degrees. So this perfectly makes sense. So if we do the calculation here for the IC, it's also the voltage divided by the impedance of the capacitor. We get something. Yeah, and so here in this case, we should get square root of 2 times 10 ampere, same value, and E2 minus J 60 degree. Yeah, because we divide by J, division by J is like a shift of minus 90 degree. And so if I do the same stuff here, calculate the absolute value of this, we get the same value. If I calculate the angle of this, we should get the minus, oh no, we get, why is this? Oh wait, because, yeah, because we have the J in there. So sorry for this. We don't need to subtract minus 90 degree, we need to add 90 degree. And so 30 plus 90 is 120. And the total current, I total is V divided by the total Z. And then we get this. And so now if we try to compare this result with what we got before here, and if I calculate the absolute value of this total current, what would you expect? That we get the 20 that we had here, and we also get the 20. And if I calculate the angle of this total current, then we should get the 75 that we had before. And we also get the 75 that we had before. Yeah, so for this total current, on the second page, I could write down, okay, this is 20 ampere times E2J 75 degree. This makes sense. Okay, so task B is also solved. If we quickly continue with task C, total current by adding IR and IC, as you already suggested before. Yeah, so now here in my solution, I've calculated the total current by the total impedance. Of course, we can also say, okay, we get the total current by adding Ri plus IC. And so let's just check it in Octave. This is the total current that we had before calculated. And so now if I say I want to have IR plus IC, we should get the same value, and we get the same value. So this perfectly makes sense. So we get the same, of course, 20 ampere times E2J 75 degree. Check. And last thing, maybe in red as a color, the currents IR and IC using the current divider rule. So I think I have some space here to write this down, or maybe I will use a new page. So in subtask D, how could we get from the total current, the current, just the current, the partial current through the resistor? How did this current divider rule work?
Impedance of capacitor divided by total impedance?
Exactly. So we take the total current, and then if we go back to the circuit for a moment, so if we want to have this current, it was, if this would be a resistive circuit, if we want to have the current going through this resistor, current divider rule worked like this. We take the resistance, now in this case the impedance of the other branch, divided by the total resistance, or the total impedance in our case of this parallel circuit in with respect to this mesh. So the other resistance or the other impedance would be ZZ, and the total resistance would be ZR plus ZC, or the total impedance. And yeah, so if I do this and insert it into MATLAB or into Octave, so the IR that we had before was this value. And so now if I take the total current, multiply with ZZ divided by ZR plus ZZ, we get the same value. So works. I will once again write this as square root of 2 times 10 ampere times E2J 30 degree. And if we want to have as the last thing, the current through the capacitor via some current divider rule, what do we need to insert now?
Other way around.
Yeah, so the other way around. So now the impedance of the resistor divided by the total impedance, which is once again the impedance of the resistor plus the impedance of the capacitor. And if I once again do the calculation here in Octave, I see this is the current that we had before. And so now if I take my current divider rule and just change the ZZ into some ZR, then we see also we get the very same value there. So it's also square root of 2 multiplied with 10 ampere multiplied with E2J 120 degree. Okay, so last thing that we can maybe do, draw the complex quantities in a phasor diagram. So we have all the values here. We once again need the total current maybe. Total current was 20 ampere times E2J 75 degree, but this is what we should also get from our complex phasor diagram. So yeah, we have something with 30, 120 and 75 degrees, so I only need the upper part of this complex plane, let's say. So this is the real axis, this is the imaginary axis. And now, yeah, I need to draw something in there that has a certain length and an angle of 30 degrees. So let me take this color for IR. And so then this should look like this, maybe. Now 30 degrees, a little more. So let's say this is IR. This current here has 120 degree. 120 degree is pointing in this direction and should have the same length. So this is IC. The angle between them is a right angle. And so now I could also shift the IC to here. Wrong color. Shift the IC to here, or I could also take the IR and shift it to here. So this is the same IR as before. This is the same IC as before. And so the sum of the two should be the total current. This is the total current. And you can see, okay, the total current is really square root of 2 times longer than what we had before. And the angle of the total current is the 75 degree. Yeah, and the remaining thing is maybe just that we would need to have the voltage here. Also in our phasor diagram, the voltage was square root of 2 times 230 volts times E2J 30 degree, and this would also point in this direction here. But would be a little longer or a little shorter, depending on what scaling factors you use. Yeah, but voltage and current at the resistor point in the same direction. Voltage and current at the capacitor have a phase shift of 90 degree. And so for the capacitor, the voltage is delayed. For an inductor, the current would be delayed. In German we have this saying, an Induktivitäten Ströme sich verspäten. To remember this rule. Yeah, so this perfectly makes sense, and then the sum of the two individual currents gives the total current. And the advantage of this way, as said, is this allows us to calculate such circuits using exactly the same rules that we used before. So series and parallel connection of resistors will work, current and voltage divider rule will work, Kirchhoff's current and voltage law will work, all the superposition, branch current, mesh current, nodal voltage analysis methods will work. The only thing is that at the beginning you need to convert from time functions into phasors. You need to convert the resistance and capacitance, let's say, into some complex impedance or admittance. Then you need to do the calculation with complex numbers. As said, if you have MATLAB, if you have Octave, it's no problem. And then at the end, finally, we would need to convert back into currents, into time functions. So finally, at the end, I will not do it now because it's already written here, but at the end we would like to have something like what is written already here, these time functions. Yeah, so one last step would be to convert these complex phasors back into IR of t equals what is written on the first page. IC of t equals something that's written on the first page. The total current as a function of time is also something that is already written on the first page. And then what is very important, and this will be the very last thing that I will explain for today, is this complex phasor and this time function, they mean the same thing. Yeah, we would like to express the same thing with them, but they are not equal from a mathematical point of view. Yeah, that's why it's not the same, it's not equal. They somehow belong to each other, but they are not equal. This is some complex phasor. It's not a function of time. There is no time in there, and it's complex valued. It's some, let's say, imaginary quantity that helps us calculating these circuits, but it has no direct physical meaning. This time function, this has a direct physical meaning. I can take an oscilloscope, push it into the power outlet, and I can measure this voltage as a function of time. So this is really a function of time. There is the time somewhere in there. Yeah, as we can see on this time function, there is really the time in there. And this is real valued because in our real life we have nothing imaginary. And so that's the difference between them. And that's a kind of importance difference in this case.